you. Welcome, everybody. I, together with Sarah Wolfaltz, are hosting this fantastic webinar today. I'm really excited that Paul Hünermund and Richard Haans have agreed to share their wisdom today. I'll just give them each short introductions. In terms of format, Paul is going to begin, and he's going to take up the first portion, about 75 minutes, and then Richard Haans is going to take to wrap things up with the final 45 minutes or so. I'm now eating exclusively into Paul's time, so just to clarify that. Just by brief introductions, and Paul is an assistant professor of strategy and innovation at Copenhagen Business School. He studies a wide variety of things, machine learning and AI strategy, organizational bias, but he's here today because of the way he contributes with great clarity to causal inference through clear expositions of data generating processes and DAGs. He is the co-founder of causalscience.org, which works on the interface of what we do here in academia and practice. So that's a very noble effort. I will note that just to point out how useful Paul's information is, he has 8 times the followers I do on Twitter, and this is for a reason. So we're going to start with him, and then I'm not going to reintroduce Richard Haans. He's going to come a little bit later. Richard is one of the leading experts on the field in topic modeling, particularly in management research. And to be honest, I know less about this than what Paul's going to speak about, so I'm super excited for this part of the session. It's just great to have somebody like Richard and people like Paul who are on the frontier and leading the way to share their wisdom with us today. So with that, I'm just going to make one little mention. Please use the chat. Should be an active thing. I know we can't really see you, which is kind of weird for us, but we'll deal. But please use, if you have a question, please raise your hand, and then we'll give you the mic. If you don't want to ask your question verbally, that's also okay. You can put it either in the Q&A or the chat, which we will be monitoring closely as we go. And with that, I'm going to turn it over to Paul.
Thanks, Brent. I hope you can hear me well. And let me share my slides. Yeah, so thanks for organizing. Thanks for the invite. I'm really happy to talk about causal inference, a topic close to my heart, and tell you a bit about this DAG stuff and what's that all about. Maybe some of you have already heard about it. It's sort of a meme on Twitter already. I will particularly focus today on something that is really relevant, I hope, for many people in the room when you do a quantitative research regression analysis, so clarifying sort of the use of control variables or using DAGs to clarify the use of control variables. And I will also talk a bit about the concept of identification. So, just a brief intro into where the DAGs are coming from, right, and causal inference per se. So, I mean, yeah, causal inference, I think, doesn't need an introduction. Is sort of, some would argue, probably I would too, that that's sort of the main goal of quantitative analysis in research, in the kind of research we're doing in econometrics. So, if you look at way back in the 30s, right, the founding of the discipline, here a quote from the first editorial of Econometrica. So the goal of econometrics sort of inform policymakers, legislators, managers about the likely impact of their actions by uncovering quantitative relationships and statistical data. There you already see likely impact of actions. I will clarify that a bit more, but that is what causal inference is about. It's sort of an interesting intellectual history. Causal inference fell a bit out of fashion, maybe in the 70s and 80s, but now is back full force, right? I mean, there was a Nobel Prize for causal inference. SMJ has this editorial about taking causal inference seriously. So it's definitely something that that we're concerned with. At the same time, very interestingly, there was sort of a separate or isolated development in the computer science literature, also starting around the same time, let's say end of the 80s, early 90s, taking causality seriously as a topic in AI. Well, things like Markov random fields and Bayesian nets and so on coming from that. Well, the interesting part, first of all, is that if you dig into that, you see there's a lot of common neutral ground, like intellectual roots with econometrics and the social sciences. But then sort of two separate streams that are emerging, right? And perhaps the goal for today is, and my work that I'm doing that on the methodological side is sort of perhaps bringing the two back together, or sort of do a little bit of boundary spanning across fields, because I think we can learn a lot from each other. So, well, the aim for today is really give you just a glimpse into the DAGs. What I will talk about today is one very useful application, but it's definitely not also. The references that I shared with you might have been a bit heavy on the technical side, but there you get an overview of what this framework can do. As I said, I will focus on a particular application today. That is about control variables and regression, but I think that's a very useful one to start out with, because, well, there's lots of mystery around regression controls, both in econ and in management. In management, perhaps a bit worse even. Well, don't want to get into that discussion, but things like if in doubt, leave out, that some of you might have heard. I don't think that's actually a good advice when dealing with control variables. So hopefully we can sort of clarify this today a bit more. Well, just to give you a bit of background, like why do the computer science people care about causal inference, causality? Well, this is something here that keeps them up at night, right? So let's say we're in the future we'll be able to program a robot, develop one that is moving, you know, automatically. Well, how can we prevent such a robot from making stupid mistakes, such as you know, shaking the rooster at 3 a.m. At night in order to make the sun come up, right? Let's imagine there's a robot or an artificial intelligence is overseeing a bunch of plots of land, and the target function is sort of growing crops, right? At one point, this AI finds out that sunshine is really good for growing crops. So we want to make the sun appear perhaps more often, maybe 24 hours a day if possible. Right, and well, what prevents this robot from doing exactly this here? You know, because the AI always observes constant conjunction, you could say in Humean terms, right? So a correlation between this little animal next to the plots, right, crowing, and perhaps 30 minutes later, the sun is coming up, right? And well, if that AI is interpreting this correlation in a causal way, we could just make the rooster crow by using force. Then we could achieve to get the sun come up. Well, for the AI, that would be great in this case, right? So deliberately silly example chosen here because this is something that you could explain to a 3-year-old probably, right? And the 3-year-old would immediately find out that this is sort of flawed logic, but it's a surprisingly hard problem from a computer science and AI perspective, because well, yeah, causality is this concept that until recently we didn't have a good sort of framework, a mathematical representation of this concept, right? And we also see it sort of in the philosophical literature that, you know, we've debated the concept of the essence of causality for 2000 years, definitely since Aristotle. And I don't know whether we've made so much progress. I leave that to the philosophers to decide. But definitely sort of the representation part, the mathematical representation was missing. So The goal of the computer scientists is to go from the robot overloads here, the very violent ones, to the nicely behaved robots that leave the rooster alone. Well, so Judea Pearl, which is a big name in that area, he won the Turing Award, which is sort of the Nobel Prize in computer science. Said it this way: to build truly intelligent machines, we need to teach them cause and effect. And that is because, well, causality is such a fundamental concept in human thinking, right? So let's not debate the essence of causality, but I think it's pretty clear that sort of cause and effect is this kind of concept that we apply on a day-to-day basis. I was mentioning the 3-year-old that could probably solve this rooster problem already. Right. And well, current ML and AI techniques that we're having, they are well, almost exclusively prediction based, right? The bulk of it. We have this awesome book by Agrarel Gans and co-authors that is called Prediction Machine, right? So that already the name tells you that well, it's a technology to make predictions based on underlying correlations in the data. That data can be high dimensional, right? It can incorporate lots of information, and that's the beauty of it, right? Like high dimensional pattern recognition, but it's still just a pattern that you pick up. And one of those patterns might be the rooster and the sun correlating with each other, and you need to rule out these sort of cases. So what we need is a framework that is able to capture this asymmetry of causal relationships, right? A correlation is always something, well, symmetric. Causality, on the other hand, asymmetric, right? It's, well, if at all, it's the sun that makes the rooster crow, right? Because the rooster is anticipating the coming day. And not the other way around, right? So this is an asymmetric notion that we need to bake into sort of the AI systems that we're having. Well, and because it's such a fundamental concept to us, if we want to interact with this future robot in a meaningful way and avoid these kind of errors that I've pointed out, they should probably have at least some notion of cause and effect. There's also sort of a catch for us, right? So why should we care as social scientists? We're not so much in the business of AI and developing robots. Well, here's this quote by, I'm not 100% sure whether Albert Einstein actually ever said that, but it's attributed to him. If you can't explain something to a 6-year-old, you don't understand it yourself, right? And he have just crossed out the 6-year-old and put in a robot, because by solving this kind of representation problem, having a framework that can mathematically capture something like causality, we probably learn something ourselves in the process, and hopefully I can tell you a bit what this something is in this talk. Okay, so much just for the background. I was really rushing here. This intellectual history is actually a fascinating one to me, but that's just to set the stage, because the actual goal is to give you some more methods or research tools that you can use in your own research. So I would just jump right in, and if you have questions on the way, I see there's already something in the chat, but then just raise your hands and we can take that right away. So this mathematical framework that I was talking about is actually one that looks quite familiar to us in management, because this framework, well, it's called in this literature a structural causal model, but what it actually refers to is, or you could call it a non-parametric structural equation model. Okay, and structural equation models is something that many of us are familiar with. So imagine we're just dealing with a very small system of 3 variables, z, or x, y, and z. Those are on the left-hand side. These are our endogenous variables that we want to explain, right? And the values of these variables attain, the values that will end up in our spreadsheet as columns in our data set, are determined by, well, a set of functions. You see those here, fz, fx, fy, so the corresponding functions. And those functions take arguments. One kind of argument is, well, you see again here those endogenous variables like z that appeared here on the left-hand side also appearing on the right-hand side. And if that is the case, we say that, well, Z exerts an influence on X, so Z is a cause of X in a direct sort of stimulus response way. Okay, so if I wiggle Z, I can change X. The second kind of argument are those U's in here, and those are other causal determinants of Z and X, for example, but we're saying that, well, we're not able to observe all of them, right? Nature moves in mysterious ways. So some of those causal influence factors of Z, X, and Y, we are unobserved to us. Okay? So yeah, that is similar to like an error term, you could say, in a regression, right? This error term is also like another influence factor that leads to that, you know, our data points are not exactly on a regression line, for example. But I just want to stress here the causal interpretation. It's not just an approximation error, right, of a regression line or something like that. It's actually unobserved causes that are outside of the model. Mm-hmm. So we also call these unobserved background factors. Okay, so it looks similar to a structural equation model, but not quite. So these Fs here, these functions, right? Well, they are the causal mechanisms in our model, but they're not necessarily linear. So they're not necessarily linear functions. They could be anything. Yeah, that's the first difference to a standard traditional structural equation model that mainly deals with linear functions. Well, and the second difference and that's why it's a non-parametric structural equation model, we also don't make any assumptions about the distribution of those error terms. So there's no assumption that this is a normal distribution or this is distributed according to an extreme value type 2 distribution or something like that, all these kind of parametric error assumptions that you have in the literature. So we want to keep, so to say, fully agnostic about that. We don't make assumptions about the shapes of these Fs, can be anything, and we don't want to make assumptions about the distributions of those U's. And that makes the framework quite flexible. If you do that, if you restrict yourself to just that, okay, so you're not saying, we're not dealing with linear functions, can be any arbitrary function, it can be any distributions of those background factors U. The information that is encoded in the system, you can actually capture via this graphical form on the right. So the right is, well, it's a nice picture, right? But a graph has a specific meaning in mathematics. A graph is actually a very simple object. Let's say a graph G. A graph just contains or consists of nodes in a network. Those nodes are usually denoted by V. Those are the variables in our model, okay? That could be, I don't know, the firm size and whether that firm is active on the stock market or these kind of variables. The second thing that a graph consists on is, well, relationships between those nodes. And here in a specific form, namely in a directed form. So if we say that Z is a cause of X, well, then in a graph, we put this little arrow here that denotes that Z is a cause of X. Okay, and well, that's it. That is a graph mathematically. So the first mystery about what this DAG stuff is, we have solved, right? It's just a depiction of those causal relationships that we assume to occur in reality or in our model. Well, the second part I've also already mentioned, right? So this graph is directed because, well, causal relationships have this asymmetric notion, right? If Z is a cause of X, we want to rule out that X is a cause of Z at the same time, because, well, it's either the rooster causing the sun or the sun causing the rooster to crow. Yeah, the only thing left then, in order to define this or clarify what these directed acyclic graphs is, we have to talk about this acyclicity property. Well, an acyclicity in a nutshell just means that if we want to rule out that if Z causes X, X is a cause of Z at the same time, right? So we want to have this asymmetric notion of causality. Then we also need to rule out that there's sort of larger feedback loops. So something like if Z causes X, X causes Y, and Y causes Z, well, then we would have, again, this kind of cyclic causality brought back in via, you know, like a larger chain, and we want to rule that out too. And if you do that, so if you say that whenever we visited one node, we don't want to have a directed path that comes back to this, that's what an acyclic graph is about. So we want to rule out these kind of feedback loops that I mentioned: A causing B, B causing C, C causing A. Yeah, this is excluded from the framework because we say that at least in an instantaneous way, right? Like at the same point in time, let's say, this is, well, actually not compatible with the laws of physics, even, right? Like something cannot be the cause of itself in the same instant of time. What there can be, of course, is sort of feedback loops over time, right? So let's say investment in last year causing sales today, and sales today feeds back into investments today, right? So that's, of course, possible in a dynamic sense, but then we would treat those variables like investments last year and investments today as two separate nodes or two separate variables in this framework. Okay, so dynamic models are not ruled out, but we are ruling out these instantaneous feedback loops. There are actually, because well, with the management count, it might not be so difficult because we're not always dealing with you know, simultaneous equilibrium models so much in our research. The economists are sometimes a bit wary about that, because things like you know, a supply and demand model is often simultaneously determined, or a game theoretic model or something like that. I just want to say that there are extensions of this framework also to cyclic graphs, if that is the appropriate modeling choice. But I will not get into that today, so I will stick to the plain vanilla DAG framework. Okay. One last thing that I should mention here in this framework that we need as sort of notation is, well, I've talked about what these edges mean. It's just cause and effect relationship, Z causing X, but there's also this, well, this dashed arc here that actually has two arrowheads, both Z and Y. This is a shortcut notation saying that, well, there's some unobserved variables that are in this set of UZ and UY that are jointly affecting Z and Y. If you know standard structural equation modeling, you would interpret this as an error correlation between Z and Y, and that's fine for the purpose, right? But again, stressing the causal interpretation of there's some unobserved variables that are jointly affecting Z and Y, and that are denoted by this by these bidirected edges, so-called semi-Markovian model, but the terminology doesn't matter so much here. Okay, so keep that in mind, because this is actually important for clarifying, well, the notion of bad controls, for example. I will check the. Okay, so it's the messages from Ryan. So no questions at this point. Then I can continue and tell you why this framework of DAGs is actually useful. Why have I spent now, I don't know how much it was, 15 minutes or so to introduce this framework? Well, it's useful because there's a close connection between those graphs and the way they're structured. We also say the topology of the graph, and stochastic relationships between those variables that we try to model. So the variables that represent the nodes in our graph. And this relationship is called the D-separation criterion. And in order to introduce it, we can just look at the three canonical cases, right? So let's say we have three variables, A, B, and C, and they can relate to each other in three possible ways, right? We can either have a causal chain where A is a cause of B and B is a cause of C, so sort of a proximate causal relationship. We can have a fork where B is jointly affecting A and C. We also say that B is a parent node of A and C. Yeah, so jointly affecting fork, that's where the name is coming from. And we can have exactly the opposite, a collider, where A and C are just two unrelated variables, but they jointly load or they jointly affect a third variable B. Okay, so these are, without just loss of generality, these are the three possible configurations. And now we can think about what this means for actually, for example, correlations between those underlying random variables. And I think it's sort of pretty intuitive that if A is a distant cause of C, right, A affecting B, B causing C, or also an ancestor of C in this kind of graph language, well, then A and C in general will be correlated. Okay, in our data set, A and C will be correlated because A transmits at least some effect on C. This is, captured by this notation here. This kind of column operator, right, is saying two variables are orthogonal. Orthogonal means they are uncorrelated or independent. If I cross that out, I'm saying they're dependent. So stochastically dependent, which is a more general notion of they're correlated. So if you don't, if you're not very familiar with this terminology, just think about, okay, this means they're correlated. This means they're uncorrelated. That's, for the purpose of this talk, it's totally fine. Okay, but now comes the catch, or what we will exploit is that, well, if A and C are correlated, but I could somehow block the influence of this middle node B, and in a stochastic sense, I could do so by, for example, conditioning on B, holding B constant, or controlling for B, for example, in a regression. These are all sort of equivalent ways of doing this adjustment. Then, well, A cannot transmit an effect on C anymore. So if we condition on B, and that's the notion here, then A and C will become independent or uncorrelated because we've held B constant, so A cannot transmit an effect on C anymore. A similar pattern actually emerges for the fork, and I think it's again rather intuitive that let's say if A and C, right, are two siblings and they share a parent, right, then perhaps intelligence of these siblings is sort of correlated in a large data set, right? The same, right? I mean, if two variables are affected by a third, then they will generally be correlated with each other because B transmits something on both of those. So A and C again will be correlated. But if I condition on B, hold B constant, again, what is left of A and C is actually independent because I've sort of blocked this influence of the common parent B. So then again, here for this fork, A and C will be independent or uncorrelated, conditional on B. Yeah? So the chain in the fork, actually, in a stochastic sense, they operate exactly in the same way, although there's a different underlying causal structure behind it, right? So these structures here on the left-hand side are different, but this would be observationally equivalent. That's different, though, with the collider, and that becomes interesting because, well, a collider, A and C, those variables, they're actually independent of each other, but they load on the same variable. And if I now condition on B, I actually create a correlation between A and C. So the collider works in such a way that A and C, well, it's exactly the opposite. They are independent, uncorrelated. But if I condition on the middle node B here on the right-hand side, A and C will become dependent. It's also sometimes called the explaining away property. And well, that's a bit less intuitive. So I give you an example here. So this is taken from a Nature paper. In 2020, they were thinking about, well, COVID disease risk factors, but the example that they use is actually not related to COVID at all. It's about admission to college in the US. Right, I think well, the example wouldn't work so well in Europe because we don't have academic tracks as we don't have sporting scholarships at European universities. That's what I want to say. But okay, probably many from the US in the audience, so that works well. So think about two possible ways of getting admitted to college, right? So you can either be very smart, meaning that you're scoring very high on this x-axis here in terms of academic ability, or there's a second possibility that you're a good gymnast, or you're a good football player, or you're good at rowing or something like that, because well, the college has sort of an athletic team that is admitting students based on their athletic ability or sporting ability. Right? And for the sake of the argument, let's assume that those two are totally uncorrelated in a general population, right? So there's no correlation between academic and sporting ability. You see that in the scatter plot here. If you look at all these points that you run a regression through, that would be the blue line here, then there's almost a zero correlation, right? Almost no slope. Now, though, if you look at a sample of students that have been admitted to a specific college, right, that applies these two modes of admission, those would be the red points here in this example, then you actually find a strong negative correlation between the two. So suddenly, by conditioning on a middle node, sporting ability and academic ability in your data appear to be negatively correlated. What's the intuition for that? Well, if you're very smart and you get admitted based on your SAT scores, you probably don't have to be so good you don't have to be a great football player to be admitted. While the other group of students, right, tends to probably score high on athletic ability, but perhaps not that high on academic ability. So this creates this negative correlation between those two variables. And well, that's not due to a causal relationship, right? There's no causal relationship assumed here between the two. That's just simply a statistical property. Right? So these collider nodes or these collider structures, they're actually quite tricky, and we will see them popping up quite a bit in what follows. So yeah, just to come back in this sporting and academic ability example, the middle node would be being admitted to college. If we had more time, we could also run a little simulation in Stata or R or even Excel in order to show that. But yeah, just want to stress again that the collider works exactly different to the chain and the fork, because here the middle node creates a correlation between A and C that wasn't there otherwise. Okay, so these colliders can be tricky. We will see it, and sometimes some people have called them the landmines of empirical research, because it's a bit like, if you step on them, bad things will happen. You will see that they play a big role in the notion of bad controls that I will introduce you to. Stopping again here, if there's some questions. At the moment, I don't see the chat. Okay, there's nothing there. Then we can continue. Okay, well, I will be very briefly on this point, but I promised you to clarify what this meaning of identification is, right? And sometimes this is used, we use it all the time. Something is identified, can you really identify an effect? We use this lingo all the time, and it took me actually quite a while to figure out what people mean by this, because it's sort of this ancient terminology that changed meaning over time. But I think the DAGs make this notion pretty clear. So what we're after when we do causal inference, well, we don't want just to passively observe a system, right? We don't just want to passively observe that a certain company has implemented a working from home policy, and how does that affect, for example, collaboration within teams or something like that, right? That would be this case here. Here on the left-hand side, this is sort of what we call the data generating process that is just coming from nature, right? We are not actively intervening in that. When we do causal inference, we want to do something else. We want to actually, we want to intervene on certain variables. Let's say we want to implement a working from home policy in a certain company, right? And then we want to check what this intervention has as an effect on other variables like team collaboration. Right? So what this intervention means in a technical term is, well, before we had, if X is this working from home policy, before whether someone worked from home was decided by some causal mechanisms that were out there in the world, right? Now, if we deliberately intervene on that, we are breaking this dependence, right? So we're getting rid of this fx function that was there before and set x to a specific value. So if working from home is a binary variable, we would say, okay, either all employees or just a specific group of employees is sort of forced to work from home, while the others is forced to come to the office, and we will compare the collaboration patterns within those two teams. Yeah, whatever there was of a dependence before that z affected x, we break this, we get rid of this this error in the model, and set x to a specific value. Here is also the notion of treatment and control, right? So if X is taking a pill in a randomized control trial, for example, then well, setting X to the value 1 would be equivalent of taking the pill, while 0 would be getting the placebo treatment, right? So there's a tight notion between those two. This well, operation of doing an intervention, not just passively observing a system, but actually intervening in it, and checking well, what influence that has on other variables in the model is captured by this so-called do operator. The specifics don't play so much of a role for us, but what we then want to see is, well, we want to actually measure other variables in the system, again, some outcome variable like team collaboration, and how that outcome responds to this kind of treatment that we've established in doing this intervention. Okay, so that's the goal of causal inference. We intervene in the system and then want to ideally see an effect of this intervention on certain other variables. Well, the identification problem comes in because, well, often we're not able to do this sort of hypothetical intervention that I've described, right? We're not able to actually do that, right? Sometimes we might be, if we're able to do randomized control trials, then sort of this causal effect becomes immediately observable to us because we've done the intervention ourselves. But even with, you know, experiments, there can be, you know, strings attached like selection bias and these kind of things. But what I will mainly focus on here is the case where randomized control trials aren't possible because perhaps they're too expensive, they're simply impractical or unethical, right? And if we do well, regression analysis, that's often the case. The identification problem then is, well, we have something, this kind of do operator here, right? So we want to measure the effect of an intervention that we're not able to carry out ourselves. So we have to answer a question about a hypothetical intervention with data that only comes from passive observation. Okay, we only have passively observed data available, but we want to say something about the effect of an intervention, about a causal effect. Well, and then we know that correlation does not imply causation, right? So in general, like a correlation between two variables doesn't refer to a causal effect. So what we need to do, and that's the identification problem, we need to translate this causal effect of interest here into something that we can observe and that we can measure or estimate from data. Okay? Spoken in a bit of an abstract way, but that's what we're after. We want to translate a causal effect that is not immediately observable to us into something that we can actually observe in passive, passively or in observational data. That's the term I was looking for. Well, and then we face all sorts of problems in this identification problem, and the one big problem that we're dealing with all the time is confounding bias. Right, and here's a simple situation. Let's say we're interested in the effect of a variable x on y, and I've already put down here this this causal arrow down here. Right, x has a causal effect on y, and this is what we want to get from our data. At the same time, we based on theory or prior background knowledge, we presume that there are other variables out there, like for example W and Z, that also exert an effect on these variables X and Y that we're interested in. And here in a specific way, so this DAG that I've put down here would say that, well, there is a direct causal effect of X on Y. This is what we're interested in. But then there's also this, this indirect effect of Z on X and Z on Y. And if you remember the deseparation criterion, right? So going back this part here, well, this looks very similar to a fork, right? It's actually a combination of a chain Z, W, X and a fork between Z and X and Y. Okay, so the deseparation criterion can be enlarged to larger graphs and sort of add up in that way. So in this graph, what the result would be is that, well, the effect of X and Y is called as confounded by these other two variables W and Z, because those variables create a spurious correlation between X and Y due to the deseparation criterion, right? If you see this as a fork, then well, X and Y are correlated simply because they're connected by this upper path up here, this fork. So this path here connecting X and Y creates what we call a confounding path that leads to the situation that well, X and Y will be correlated even though there might be no causal effect between them at all. And that's the bias, that's the confounding bias that we need to deal with. How do we deal with that? Well, again, the deseparation criterion gives us a way out to do this, because we said that, and I'm jumping back, if we have this fork, then yes, A and C will be correlated due to this fork. But if we condition on B, control for B in a regression, then we can break this dependence between A and C and well, shut down this correlation between A and C. That's the property up here. So going back to this graph here, yes, we do have a spurious correlation between X and Y that is created via this upper path. But if we can condition on one of those variables here, actually either Z or W, then we can block this spurious path and by that actually achieve identification here in this case. So that is the idea of introducing control variables in regression that we will talk about for the remainder of this section. The last thing I should mention, because it's so again terminology, these, let's say, these tricky paths or the paths that are creating this confounding bias here up, this one here, right? Those are always paths that are pointing into our treatment variable X. You see here this arrow from W to X. And they're not emitted by X, because the paths between X and Y, where there's an arrow from X to Y, that is the causal path that we're interested in. All the spurious paths, actually, they point into X. They are, well, reaching X via some other variables. And because they're pointing into X, they're also called backdoor paths, because they're entering X sort of through the backdoor. Okay, so whenever we have a connection between X and Y, where the last arrow is pointing into X, we call this a backdoor path. And those are the ones that are causing the trouble. Mm-hmm. So compared to the actual causal paths where X is emitting those arrows. So we need to distinguish those two from each other. Well, and what's our strategy to deal with this confounding bias? We will identify all the backdoor paths that are pointing into X, and we will try to close those backdoor paths by conditioning on some of the variables on those paths. Here, in that example, that could be either W or Z. Both of them actually work. That's the idea in a nutshell of control variables in a regression. To well, make this more concrete, I put down here a definition that looks a bit ugly maybe at the beginning, but let's go through this and then it will become clear. So what we are after, and this is the so-called backdoor criterion, is we are starting with a directed acyclic graph. We're determining a set of variables x and y that we're interested in, because the effect of x on y. And we try to find a set of nodes that are blocking all the backdoor paths between x and y. So in this example up here, we have x and y as our treatment and outcome variable, and we have one backdoor path, and we want to find a set of nodes that blocks these backdoor paths, given the deseparation criterion. If we're able to do that, if we're able to find such a set of variables that block those backdoor paths, well, what can we do? We actually can solve the identification problem with this mathematical result down here. Now that looks a bit too abstract. You have to just think about this in more concrete ways. If we're able to find a backdoor admissible adjustment set that blocks these backdoor paths, we can just include those variables in the regression, and then we're able to solve our identification problem, because then we're able to translate this kind of causal effect that is unobservable to us with something that is observed here on the right-hand side. Okay, that was a bit abstract, so I will try to make this now more concrete with an actual example. So think about standard skill premium problems. So you're interested in the effect of people being admitted to college or going to college on future earnings. Why? Okay, and let's say we have this directed acyclic graph on the right-hand side. We have other variables like the occupation of an individual, work-related health, and some socioeconomic factors that are related to those variables, and that they're related exactly according to this model here on the right-hand side. What we're interested in is the effect of C on Y. Okay, but there's, for example, one backdoor path here on below, where E is jointly affecting C and Y. So these socioeconomic factors like parental education, for example, would affect both whether someone goes to college and have an effect on future earnings of the individual. So, here's definitely one backdoor path that we have to deal with, because this backdoor path is creating a spurious correlation between C and Y. So what do we do according to the backdoor criterion? We want to find a set of nodes that is blocking all the backdoor paths between X and Y, while simultaneously leaving all the other directed paths intact. So if we look at this, this example again closely, we see that, well, the only edges that are pointing into our treatment variables C here, I cannot highlight this unfortunately, are going by E. Because all the other paths up here on the north side of the diagram, you see they're actually not backdoor paths. They are emitted by C. So these would be indirect causal paths that affect Y in an indirect fashion. So for example, if you go to college, that makes it more likely that you will end up in a certain high-paying occupation, let's say, a white-collar job, and that will affect your future earnings, right? So there's an indirect effect here. The same if you're working in a white-collar occupation, that will have an effect on your work-related health age, and that will also have an effect on your earnings, on your lifetime earnings, because healthier individuals probably make more money. Yeah. So, and this is the way to go about this. You're inspecting this directed acyclic graph. You're trying to figure out all the backdoor paths. You want to block those while leaving the other directed paths that are connecting C and Y in a directed way, leaving them intact. So those you don't want to block. So in this example, it turns out the the solution is quite easy because both backdoor paths here on the lower side can actually be blocked by conditioning on E. So if we control for these socioeconomic factors, we are able to estimate here in this example at least the effect of college degree on future earnings. Well, if I have more time, usually I do a little quiz at this point, and let my students sort of solve this in a quiz form, but I think we're running a bit out of time. That's why I will go through it just by myself to give you a bit more intuition again about this backdoor criterion. So here we have a graph where we're interested in the effect of X and Y, right? Again, we want to solve this identification problem. We want to find the suitable control variables for estimating this effect of X and Y. Well, first of all, what do? We go through the diagram and see that there's a causal effect of X and Y going via this variable C6. Well, this directed path we don't want to touch because we don't want to control away the mechanism of interest. At the same time, we see that there's this variable Z1 that is a direct confounder of X and Y. It's a fork, right? And due to this fork, X and Y are correlated simply because of this confounding factor Z1. So, one immediate thought would be we need to control for Z1 in our regression if that's the causal diagram that we're dealing with, which is a correct thought, but it's not the full story because, well, we have another path up here, sort of following this M path here. So that's why this is also sometimes called the M path, where Z1 is actually a collider node. So this is a quite tricky example, and that's why I love to do it as a quiz. You need to control for Z1 because it's a direct confounder. But if you do that, you actually open up a path, this M path up here, because Z1 is a collider on that path. And remember, a collider blocks a path. But if we condition on a collider, a path gets open. So again, last time I'm jumping to this slide, but just to make this clear, there's a path between A and C that the collider currently blocks. A and C is uncorrelated. But if we condition on B, A and C become correlated, this explaining away type of property that you've seen in this example here. So yes, that is the way to go about this. So you need to control for Z1. There's no way around that. But by doing that, you open up the other path upstairs. But well, as long as one of those variables, Z2, Z3, Z4, Z5 is observable to you, you can additionally include those in your regression and then you're fine. Because, well, you can open up a path, but close it at the same time again. That is actually possible. Yeah. So the way to go here would be, well, you can either include Z1 and Z2 in your regression, and that would allow you to identify the effect of X and Y. You could also go for Z1 and Z3, or Z1 and Z4, or Z1 and Z5. So you actually have a lot of wiggle room here in this example. You could also include all of them together, but that's not necessary. Right? So that's why we call this a minimum sufficient adjustment set. Either one of those sets of control values would work. And note that, well, I said you can include all of the variables here except Z6, right? Because if you include Z6 as a control variable, you actually block the actual cause effect of X and Y that you're interested in by, well, it's a chain, right? According to the deseparation criterion. So if you condition on Z6, you block the effect of X and Y, and you would find probably an insignificant effect of X and Y in your regression. Okay, I see there are some questions. Should we take something right now? What would you say, Brent?
I was able to respond to it in the chat, but you can take a look as well in case you want to elaborate. I gave a very curt response.
Okay,
the question was, you know, back at your earlier diagram, when you control for Z and you control for, well, you should just read it.
Okay, yeah, I see a question about precision. I will come back to estimation precision in a second. And in the interest of time, I will maybe skip over some examples. You can actually try to solve those yourself at home. It's a nice exercise. I will I will skip quickly to this example here. Because there, I think it becomes even more apparent the sort of what a useful tool these causal diagrams are here. Because if we look at this example, it looks fairly complicated, although there are just 6 covariates out there, right? So there's X and Y, the treatment and outcome variable that we're interested in, and 6 other covariates. That would be like a medium-sized regression, right? Even in the people in the 80s were able to run these kind of regressions, right? So actually not that convoluted. Well, and here, of course, this is a sort of arbitrary chosen example, right? I don't know whether it would correspond to ever some real life situation. But if you look at this graph over here, you can actually find the backdoor admissible adjustment sets, and they look like the ones down here. Here you have even more choice of admissible control variables or possible control variables, because the simplest way to go about this here is just to control for W2. You see that W2 basically is the endpoint of all these backdoor paths. So by controlling for W2, all the other variables become unnecessary to you. And well, talking about precision, that's actually a good thing, right? Fewer variables in your model increases degrees of freedom and efficiency. You could, in principle, also, control then additionally for other variables like W2 and W3, or W2 and W5, and so on, W2, W3, W4, W5. That's the largest possible set. So I've listed all the possible adjustment sets here. What you shouldn't control for is, well, first of all, W1 and W6. W6 we've already seen because, well, that's just explaining away a mechanism here, right? Or controlling away a mechanism of X and Y. So you don't want to condition on the intermediate variable. Why is W1 a bad choice of control variable? Well, because W1 is a collider here in this graph. Perhaps it doesn't look like it at first glance because we have these bidirected edges here. But remember, bidirected edges just means there's some unobservable variables jointly affecting X and W1 in this case. Right. So we actually do have a collider, 2 arrows pointing into W1. If we then condition on W1, we actually create a spurious correlation between X and Y. So W1 needs to be avoided here. W1 would actually be a bad control in this example. And yeah, the notion of bad controls is closely linked to these kind of colliders. Well, if we had more time, so I'm teaching that here at Copenhagen Business School in a semester-long course. After that semester, students are very well trained in sort of these kind of graph operations, right? And they can probably think about them in their sleep. And then you would be able to figure that out, in, let's say, half an hour with a pencil and paper. But you actually don't have to, because, and I give you a link at the end, this is something that a computer can do for you, right? So this kind of backdoor criterion, listing all those possible paths and finding nodes that are blocking those spurious paths, this is something you can teach to a computer. So that is the first very basic connection to the AI problem, all right? The directed acyclic graphs, there are algorithms that can solve this identification problem for you, well, you can teach to a robot, right? And suddenly a robot will be able to reason causally, but it's also just a useful tool to apply in your own research. If that example that is deliberately chosen in a way that looks a bit complicated, if that looks too complicated for you, you can just outsource that to a computer, no problem. What I want to do is, in the last remaining 10 minutes or so, I actually want to give you a short taxonomy of controls, because I think this sort of checklist is most useful in your own research. Right, and this taxonomy, well, let's first start with the good controls, the controls that we actually want to include in our regression. We've already seen those examples here. So X and Y, that's what we're interested in. And there's some either one variable or set of variables that are affecting X and Y jointly, right? Here, according to d-separation, that is a fork that is creating a spurious correlation between X and Y. How can we block that? Well, by conditioning on W. We include W in our regression, and that's why W is a good control in this example. Okay. The same goes for this graph down here. Here, the difference is that, well, W actually doesn't have a direct causal effect on Y. There's not an edge emitted from W connecting Y, but they are just related by a third unobserved variable, like unobserved variables that affect W and Y at the same time. Okay. According to the d-separation, well, this is actually sort of a chain, right? Because we have an arrow pointing into W, and W emits an arrow on X. Okay, how can we block a chain? Well, again, we condition on W, we include it as a control variable in our regression, then this spurious path is blocked and we're fine. What remains, the remaining correlation between X and Y, is the causal effect that we're interested in. So these are the good cases. Okay? Now the troublesome cases come, the bad controls. Okay, so note I go through this here in a sequential way, right? So first of all, I've replaced this direct edge W and Y with an unobserved confounder. And now I also replace the second one with an unobserved confounder. So what this actually means is that W is not a cause of X and Y. They're just correlated with treatment and outcome due to these unobserved variables. And if we just, for example, check a correlation table in our in our data or on papers, right, we wouldn't be able to discern these two effects or differentiate these two cases. Well, here W is a bad control because W is a collider. Right, again, these two arrows pointing into W at this point here. And if we include W as a control in our regression, we actually open up a path that before was blocked. A collider usually blocks a path, but if we condition on it, we open it up. Okay, again, the sort of landmine problem. Here we've accidentally stepped on a variable W that, you know, in our correlation tables looked highly correlated with treatment and outcome. So we told ourselves we should better include it in our regression. But here we would actually make the exact opposite of reducing bias. We would create more bias. That is what a bad control is about. Okay? And you can figure this out based on the d-separation criterion. Then here the middle graph is sort of the debatable one, because I'm sure some guys in the audience are sort of dealing a lot with mediation analysis, right? And that's an important topic in our own research. We could probably do another workshop on mediation analysis. So I will try to be very brief here, but in our framework, if W is not a cause of X, but it's the other way around, X is a cause of W, right? In that case, W is a mediator that sits on this path connecting X and Y. Well, then in this case, in the diagram in the middle, we could in principle control for W, because that would block the upper path and only leave the lower path intact, right? So that would allow us to sort of get at a direct effect of X and Y, right? Because the indirect effect via W is blocked by conditioning on W, and what is remaining is just the effect of X and Y. that's sort of the idea of a standard Baron and Kenny mediation model, right? You condition, you include the mediator in your regression, and you check whether that changes sort of the total effect, right? Here that works in the middle. Well, I've included it as a bad control because if you do that, you need to be aware what you're doing, right? You're not creating bias, so that's fine, at least in a linear model. You know, if we move out of linear land, then things become more tricky. But you need to be aware that suddenly it's not a total effect anymore. It's a direct effect only that you're estimating. Things become very tricky if here on the lower side on this diagram, if you also have W and Y connected by an unobserved confounder. Because then if you condition on W, yes, you're sort of blocking this mediation path up here, but you're also opening up this indirect path from X to W, and W and Y being connected by an unobserved confounder, because W is the collider here on this path. So yes, mediation analysis in the middle diagram works, but if you you know, that's a strong assumption that there's no that there are no unobserved confounders between W and Y, or like an error correlation. If that is the case, there's actually no way of identifying the indirect and direct effect. So in this case, mediation analysis will actually fail. So mediation analysis is sort of a tricky business, and probably much trickier than many of us are aware of, if you just know the standard Baron and Kenny type of procedure. But okay, I need to hurry up to get through my taxonomy. Well, the last cases are sort of the ones where there's no possibility at ever identifying a causal effect, right? So the first one is, well, if you have unobserved confounders between X and Y, so there are variables affecting X and Y jointly, but you're not able to measure them. You're not able to include them in a regression analysis. Well, then you will not be able to identify a causal effect. That's the omitted variable bias case. The last thing here on the slide, that's even more tricky, I would say, because here you are actually able to observe W, right? And W is a confounder connecting X and Y. But at the same time, W is a collider on this upper path here due to this unobservable. So no matter what you do, you know, Carlos Sinelli called this, you're doomed if you do and doomed if you don't, because you need to include W in your regression to block this fork down here, but W is also collider. So there's no way of you reducing bias by including W2, but at the same time you're creating bias. So in this case, there's no way of getting at the actual causal effect. This case is actually very similar to the one that we've discussed here, just that, well, all of these variables Z2, Z3, Z4, Z5 would be unobserved. So then, well, there's no admissible adjustment set. Okay, and the last case in this taxonomy, and I guess then I'm really out of time, is what we call unnecessary controls. Here, again, going through this sequentially, I'm saying, well, here W is either just related to X or to Y, but doesn't connect those two, okay? And well, then if these edges are missing, then there's no backdoor path, right? Because, okay, here W is pointing into X, but it's not at the same time connecting this backdoor path to Y. So these are variables that you would not need to control for, not need to include in your regressions. You could, there's no harm. Well, there is a harm, because if you have this situation down here, where W is a cause of X, you would actually increase the variance of your estimates, because, well, I will not get into the intuition for that, just trust me. But here, by including W, you would actually make your confidence intervals wider or your standard errors larger. And that is, of course, bad if you want to get something significant out. On the upper diagram here, where W is connected to Y, but not to X, is actually the exact opposite. Again, here, by including W, you would actually shrink confidence intervals, you would make estimation errors smaller, and that might actually help you to get something significant out. So if you're sure that you're dealing with this case, you can actually include W just for precision reason. But well, the catch is, of course, if you accidentally have the situation on the lower side, then you achieve exactly the opposite of what you wanted to do. Okay, I have some concluding remarks, but maybe I will leave them to you, and I will send along the slides, how you can use this backdoor criterion. I just want to refer you here to this website called DAGD. DAGD is actually a browser program that allows you to do these kind of backdoor calculations, as I said, in a fully automated way. So you can put your DAG into the program, and then it figures out these kind of backdoor admissible adjustment sets for you. So I use that all the time in my own research to just quickly check things. But it's also just a nice way to playing around with this and getting a better intuition for this kind of backdoor criterion and finding suitable control variables in these directed acyclical graphs. All right, that's what I wanted to say.
Wow. Paul, thank you. Thank you. I thought I understood a little bit about DAGs, but like this was really helpful. And so I'm just really thankful for your time and that you did that. I feel like there's a fire hose and my mouth is like wide open trying to drink all the knowledge coming at me. And
that sounds like it was also a bit overwhelming, but we actually do have.
No. This is exactly.
I just want to say we do have a paper on this. We just finished it for the AOM proceedings, so I'm happy to send that along. And for example, this taxonomy that I've put out here, we describe in this paper. So if you find that useful, please use it.
Oh, absolutely. That would be wonderful. If you could, you'll see in the chat afterwards. Take a moment and read the response to your talk. So thank you. But just to make sure that the fire hose, or not shutting down the fire hose in any way, I'm going to turn it over to Richard Haans. Richard is going to talk about topic modeling, which is a slightly different topic, but also super important in our research. And I'm super excited for this. I'm not going to take up his time, so I'm going to shut up, which is hard for me to do. And thank you, Paul, and take it away, Richard.
Thanks, thank you. Let me just set up. Okay, so yeah, I'm going to just briefly start, quickly start. Tough act to follow, I think. So just to preempt a little bit, I'm Richard Haans. I'll be talking about something completely different, I would say, than what we just saw. Topic modeling. It's a method for textual analysis that you might have seen. It's increasingly becoming popular in strategy research. I'll just walk through a couple of questions today in the little time that I have. So first, I'm just going to talk a little bit high level about what is topic modeling even. It's one of many potential text analysis methods. So hopefully I'll give some foundations there. Then I'm actually going to walk through an example to help you understand, okay, how do you do topic modeling in practice? Because it's a quite easy to use method, but there's actually a lot of choices that you need to make throughout the process as you go along different steps of the analytical pipeline, if you will. And if time allows, I'll just end with some thoughts on, okay, how do you publish these kinds of things? I've written an annals piece about topic modeling with a group of people with whom I've been organizing also other workshops. So I just want to give them some credit as well for the materials that I'll be using today. And I've also used it in my own work in the publication in SMJ and also in some less successful projects. But hopefully I'll be able to share a little bit of a sense of how do you justify using these methods, how do you report them? Because it's a whole different, I think, ballpark than some more standard quantitative methods that you might use as you do research. Okay, so let's just start with the basic question of what are topic models? What is it? And I think in just recent years, there's been a massive move towards using textual data in strategic management research, but also just in general in management research and in business research, just because of the fact that a lot of organizational phenomena, they play out or are in some way represented in written or spoken words. So there's just a lot of data out there that are textual, right? So annual reports, patents, scientific publications, press releases, policy documents, newspaper articles, organizational websites, etc., etc. So a lot of strategy-related phenomena can be captured in one way or another via textual data. And what automated text analysis specifically allows us to do is move from the words that you observe basically to numbers, right? And by converting things to numbers, you're able to generate new data that you can use for quantitative, either descriptive analysis or also in more standard regression analyses. Historically, there's always been use of textual data, but there's really massive cost involved in analyzing those collections of text for various reasons. And in recent years, there have been so many developments in terms of using automated text analysis to analyze those large bodies of text that have a lot of promise, I think, to strategic management research. So for example, just the fact that we can now process these massive corpora of textual data really has reduced the kind of cost and time investment required to analyze these texts compared to years ago, where stuff would still be on microfiches or kind of low quality scans of papers, etc., etc. So there's a really massive cost reduction. In some ways, by being automated, there's also quite a big reduction in the human intervention. So topic modeling specifically allows you to identify clusters of terms that you could also consider trying to code manually as a human reader. So that's a kind of a benefit of this approach. And because it's really systematic, it really fosters, I think, replicability. So anyone with the same code and the same data can, in theory, get to exactly the same topics. As we'll see as we go along, it's a little bit more complex than that because of the many choices involved. But nevertheless, I think it's really relative to alternative approaches to working with textual data. These automated text analyses really help you foster replicable research. And just fundamentally, I think these automated text analyses, and especially then combined with very large-scale textual data, allow us to basically measure large-scale phenomena, social phenomena, that we would simply not have been able to pick up on in the past. So topic modeling specifically tries to find in these big collections of text, these latent topics that are underpinning those collections of text. And those are quite often topics that human readers would not really be able to pick up on. And I think one really nice thing specifically also about topic modeling is that you can use it for nearly any kind of research. So for induction, right, you can estimate topics and then interpret those topics in a very inductive way. I've myself used it in a more deductive way by converting them to measures that then go into regression analyses, but also just more abductively, right, where you kind of go back and forth, if you will, between the results and then your theory, and then you go back to the model, and this can really lead to cool abductive research as well. So topic modeling specifically is a machine learning approach that can be used to find essentially summaries or short descriptions of members of a collection of text. So this would be typically called a corpus, which is efficiently processing this text while at the same time trying to preserve what this model sees as kind of the core essential statistical relationships underpinning the documents and underpinning the terms in those documents. And you can really use this for a lot of purposes. For example, it was historically developed for the classification of text. So if you have a body of articles, which topics do they discuss, right? So you're able to classify those articles. Can be used for novelty detection. So which documents were the first to introduce a topic. You can summarize documents. You can see how similar or how different documents are, et cetera, et cetera. So really a widespread potential use case for this method. And especially in strategic management research, I think since 2015, when Sarah Kaplan and Kevan Vakili published their SMJ piece, there's really been a very high uptake on this method. So I've used it myself in a paper published in 2019, and there were enough papers out there in 2019 that we already were able to do a full annals review on the method. So it's really been an exponential growth in terms of people using this method. There's a couple of key features that I want to flag for topic modeling. The first is, and that's a very important one, is that it's a so-called bag of words model. What that basically implies is that it takes a text and it throws all the terms in a bag, and it removes any kind of syntax, any sort of sequencing, etc. So it completely does away with syntax. It's also best used for identifying themes in text where you do not know the categories upfront. It's really a purely inductive approach in that sense, in terms of analyzing text. So you cannot predefine what kind of categories you're interested in. The algorithm is going to identify those topics purely inductively from the textual data. And in that sense, it's also basically what they would say unsupervised text analysis. So you as the researcher don't interact, if you will, with the algorithm in identifying the topics. In terms of inputs for the basic topic models, there's just a singular input, what they call the document term matrix, or a DTM. And that's basically this on the right. It's a simplified representation of it, but basically here we would have 3 documents. And in the whole set of documents, there's 5 unique terms. And these values in the cells are capturing how many times a given word occurred in each document. So in the first document is apple twice and carrot once. The second document has fly twice and airplane once. And the third document has and fly twice. So as you can already see here, right, there's no way of investigating, for example, that this text was that apple, carrot, apple, or was it apple, apple, carrot? You're not able to do anything with that in these models. In terms of output, so things that the model will put out for you. So first and foremost, it's going to identify the topics in the data set. So these are what they call clusters of co-occurring words or word constellations, which you could see as essentially the terms that systematically co-occur together in documents. It's also going to put out for every term in your data set, term loadings per topic. So in other words, the word apple in this case is going to load very heavily on the first topic, as will the term carrot. So this would be a topic about vegetables and fruits. And then you see, for example, for fly, it also gets allocated to both topic 2 and 3. And the meaning of the word fly will come from its co-occurrences with other terms, right? So in this case, in topic 2, it seems to be about insects. In topic 3, it seems to be about, say, airlines or airplane navigation, flying, etc. So the meaning of terms really comes from the way that they co-occur with other words in the text. And this model will also put out the topic loadings per document. So that would look something like this here. So every document in the text is going to be allocated to a different degree between 0 and 1 to each topic. So for example, here, document 1 loads very heavily on the first topic, document 2 heavily on the third one, and document 3 on the second topic. So that's basically all that these models take in and put out. And you can use this really in a lot of different ways. So I'm going to illustrate that a little bit shortly to hopefully help clarify the process a bit. But this is really the core of how these topic models operate. This is a kind of more graphical representation from one of David Bly's papers. I'll have a couple of slides with further readings at the end of this, but they try to represent the kind of the assumed data generation process. And essentially what the topic model assumes is that underlying the whole body of text is a set of topics. And the authors that write the text are basically going to first pick the distribution of topics that they have in mind for their document. So you might want to write an article, in this case, about genes. And then you're going to select the terms that are associated with those topics. And in that way, you're generating the texts. That's the assumed data generation process here. So this is one way of representing this. And then you can also represent, right, what I just said, the documents according to the topics that they discuss. So this is an actual application on scientific articles. And they, in this case, for example, identify 4 key topics for this particular article. One about genetics, which they labeled themselves, and that contained the terms human, genome, DNA, genetic, and genes, for example. Those are the top terms for that topic. Evolution, so evolution, evolutionary, species, organisms, life, etc., etc. So that's what these topic models basically put out. There's a couple of caveats that I want to flag before I get into the practical example. I think first, because topic modeling is really very easy to use and it will run on essentially any textual data, independent of its quality. I think it's increasingly as becoming a kind of black box for social science in particular. You almost do not need to know anything about the algorithms in order to run them or about the choices that go in, which is unfortunate because these models are really extremely sensitive typically to the different inputs in terms of settings and choices that you make as you run these models. So what this implies is that quite often if you do topic modeling, you actually need to take quite a supervised approach in order to get to more meaningful results. So I'll show you in the practical application shortly just how that tends to play out in practice. So what kind of decisions are you making as you go along and what theoretical implications does that have? And also it's quite important to flag that, a lot of these methods have been developed in computer science for very different purposes than how we as social scientists tend to use these methods. So how a computer scientist would see the best fitting model is generally very different from how social scientists tend to view the best fitting model. So this is a really important distinction to keep in mind as you think about, which topic model should I use and how do I need to make the decisions in terms of coming to the best model for my purposes. So basically what that entails is that, the automation that this method introduces, it really should never replace you having a very good understanding or an extremely deep understanding of the texts, where they came from, and also the topics, etc., that come out of these models. So essentially any topic modeling that you do will really require very heavy context-specific validation. So for example, Sarah and Kevan, they have a really good appendix also where they describe the process in terms of validating their topics. So this would typically involve, hand coding the topics by researcher. You need to request experts to code and validate the topics that you get. You would need to do interviews with the people that generate the text or with other kinds of experts. And this really involves a lot of interpretive uncertainty. So basically what I would want to flag here is that any topic model that you run, it will be actually quite difficult to make the different decisions to come to the best model, if there even is a best model. Okay, let me just quickly pause. I've been keeping an eye on the chat. I don't think I saw any questions. No, great. Okay, so let me just walk you through a kind of a practical application of the topic modeling, because I think that's really the best way to learn these methods, to just play around with them to see, okay, what changes as I change different settings, make different choices. And basically when we did our review for the annals, how we viewed this whole process is what we call a rendering process. And the rendering process for topic models, but I think also more generally for any kind of automated text analysis, is that there's 3 core rendering steps that you engage in. The first is what we call rendering corpora. And this basically entails, selecting the data that you're going to be analyzing and also trimming and cleaning that data. Then there's rendering topics. That's more specific, of course, for the topic model, but that's basically deciding, okay, which algorithm am I going to use? How am I going to fit the different model? How am I going to compare different runs of the model? Those kinds of questions. And then third, you're going to use the output to render theoretical artifacts, right? So in any, I think, strategic management application, you would need to move beyond just running the model into really substantive theoretical interpretation of those outputs. So that means you're going to create outputs, you're going to build theory with those different artifacts that you can create. And I'll just flag a few as we go along. Basically, this rendering is the process where you move between these 3 different rendering steps in a very iterative way. So you see the arrows going both ways. And that's really the reality of working with this kind of data and with these kinds of methods. So we'll see that if you change something on the corpus end, for example, all the subsequent steps will also yield different results, yield different topics, different best fitting models, etc., etc. So it's really a very iterative process, this rendering process. But basically, you can see this rendering as a kind of analysis pipeline, where you as the researcher, as the analyst, are going to make modifications iteratively as you move along those different rendering steps. So in terms of rendering corpora, it's been long acknowledged by computer scientists, but I guess by anyone doing any empirical work, is that you need to always pre-process your data before you run anything, right? So most natural language processing tends to be 80% pre-processing. So anything you put in these models that's garbage will lead to garbage outputs. So it's really a major part of the textual, analysis process, which I think quite often goes a bit underappreciated. But really, natural language processing is for the vast majority pre-processing. This process of cleaning, unfortunately, because it's rather underappreciated, tends to be full of different theoretical and methodological assumptions. And each of these will have differing implications for what you get out of these models. But there's not really any sort of set standard for how should you pre-process text. And in order to make sense of these things, you will really need to engage very deeply with the data in order to assess the quality of it, make different choices about how to clean it or not. And that's really very time consuming and very difficult. So in terms of selecting textual data, there's a couple of key questions that you need to think about. So which text do I even include in the corpus? What's the source of them, right? If you work with newspaper articles, what kind of outlets do I use, etc. Those kinds of questions. Do you need to account for differing languages, different authors, the sources of these documents, those kinds of questions. And then as you trim the data, meaning you have your data selected, you'll need to clean it up. So this would mean converting it to a corpus so that the topic model algorithm will be able to work with it. You can use various pre-processing techniques, for example, removing stop words. Those are extremely frequent words like the, and, etc., that don't really inherently have meaning, but are extremely frequent. You can also choose to standardize or maybe transform words. So for example, stemming reduces the words to their stem. That really edits the data quite substantially. You can do things like lemmatizing, all these kinds of things, converting them to n-grams, removing infrequent terms, removing extremely frequent terms. These are all different cleaning choices that you need to make as you do this work, where unfortunately there's really little to no guidance in the literature. But as we'll see, this really has quite substantial implications for what these models do and what they put out. Just to give an illustration, I'm going quite fast just to make sure I make it in time, but I've made a small GitHub repository. I'll share the link, I guess, also in the chat, where you can find both the full data that I'm using in this illustration, as well as the code for doing this. So I would urge you, if you're interested in this method, to just check out this page. You can also find some materials from my other workshops and just play around with it. I think that's the best way to understand these methods. But in this particular example, in terms of selecting the data, I'm working with websites from biopharma firms, specifically in 2020. Those were all firms in Compustat, and that leads to about 318 websites in total. And what I did was I grabbed the front page and I grabbed everything which was one click deeper, meaning, on the front page, there will be a link to About Us. So that page will also be collected. So why am I using websites? In this case, I'm using it because I will want to, at the end, kind of replicate my own paper where I was measuring strategic positioning of these firms using topic modeling, using websites. That's kind of theoretical reasoning for this. In terms of why am I using biopharma, no particular reason. It might be interesting given the COVID situation, right? It might pick up on something there, but no real theoretical reason, just purely illustrative purposes. Why am I using firms in Compustat, right? That implies that I'm sampling from publicly traded firms. So that's a specific type of firm. Mainly in this case, convenience, right? The Compustat lists website for quite some of the observations in the data set. And moreover, I can also then link it to the financials in Compustat. So it's really a practical consideration. Why 2020? Again, no clear reason for this case, just purely illustrative. But it's really important, I think, to reflect, if you do any sort of serious, if you will, application of these methods, to think through these kinds of questions. Of course, this should be no news to anyone doing research, because this is the same as choosing your sample for any kind of research. But nevertheless, it's really important to highlight, I think, that this also really very much plays a role for this method as well. So this is how these things look. On the left-hand side, we have a website. This was Merck in 2020. And on the right, you see how the textual data looks after some just basic, removing the HTML and the likes. So this is the key, the input for the textual analysis. So this is just the front page of Merck, as well as any click that stays on the same Merck domain. Then in terms of trimming the data, in terms of cleaning the data. I'm just doing some basic cleaning. The code is all online again, but I'm removing numbers, I'm removing punctuation, making things lowercase, because else the algorithm won't recognize that a word starting with a capital letter is the same word as the one with the lowercase. I remove stop words, which is the standard practice. I'm also stripping white space just to conserve some memory. But here's the code that you would want to use for that. I'm not going to belabor what everything means, but again, just have a look when you have the time and walk through this example. But basically here, I'm just doing very, very basic cleaning. So I'm barely touching the data. I think the most major change here would be to remove the stop words. That's really almost a necessary thing to do these kinds of analyses, else the stop words will be in every topic. What this results in is basically a set of 100,000 unique words. And we can already see some issues here because the longest word has over 4,400 characters. I mean, I'm not a native speaker, but I don't think there are terms in the English language with this many letters. So this is probably flagging already a little bit of data cleaning issues here. But for now, I'm just going to continue as is. So here there's a couple of considerations, right? We use the stop word list from R. So R has a built-in, or the package for text mining has a built-in stop word list. And this list is different from the list in, say, other software. So I'm using R because it has a really nice package for topic modeling. If I use Python, I would probably use NLTK, the Natural Language Toolkit. And there is a different set of stop words. So if I just kind of naively use, say I remove stop words, it can have really different implications for what kind of words I use or remove and what kind of words stay in my data. I'm also working with HTML, and these are, websites from different sources. Those are typically quite unstructured and of differing quality. And then the conversion of that to text will still lead to a lot of junk. And we'll see a little bit of the junk soon, as well as really unique terms that are specific, say, to the firm and that don't occur in any other page. So a key question there would be, do I want to remove that or not? In this case, I'm not doing anything, right? But I could maybe consider removing some of those kinds of text. And also, if you visit websites, almost any website contains just boilerplate text, right? So these days, any website would have this pop-up about cookies, legal terms and conditions, all those kinds of things. Should we remove this or not, right? So it really depends on what you want to do. And you might want to remove other terms, right? So at this moment, we don't have any kind of priors in terms of, okay, we want to remove something because we are taking a very exploratory approach. If you're maybe not interested in certain things, you might want to remove those upfront. And once you remove things, they of course cannot come back in the topics. Moving then from the corpus, let's assume now it's clean. It's not, but let's assume so, into then rendering the topics. You first need to make a decision, okay, which topic modeling algorithm am I going to use? So topic modeling is a class of algorithms. And the most basic one, if you will, is what they call latent Dirichlet allocation, LDA for short. But there's other models and typically better models out there. So for example, there's the correlated topic model, which I'll actually use in a bit. There's what they call structural topic models, which allow you to not only use the document term matrix, but also bring in covariates in the estimation of the topics. And there's many more other kinds of topic models out there. So that's a really important decision to make, based, of course, on your research interests. And then there's also different configurations of these models. So even the same algorithm, you can estimate in different ways. So almost any topic model will require you to specify how many topics do I want to estimate. And every algorithm will also have its own specific settings. And these settings, when you change them, will also lead to different results. Once you make these decisions, you will, of course, then run the algorithms. And then you need to decide, okay, which of the different specifications that I ran is the best fitting. So there's a couple of quantitative measures of fit. So I'll show two in a bit, semantic coherence and exclusivity, but there's hundreds of other fit statistics out there. So how do you determine then which statistic do I even use? But at the same time, also you need to ask, are the topics that I get out, are those meaningful? So that's a more substantial validity of the topic models. So a very well-fitting model can be completely junk in terms of the topics. So that makes it kind of multiple things to consider there. In terms of our own illustration, I chose to use the correlated topic model. It's very similar to the basic topic model, but it just relaxes one assumption, which is that the topics are uncorrelated. So some work has shown that it leads to better quality models. So that's kind of a statistical reason to use this model. There's also a practical benefit in that the STM package that I use in the code is an extremely user-friendly package. So if you want to do topic models, it's really a very nice usable package. And by default, it also estimates the correlated topic model. So that's a more practical reason to use this model. But also here, there's different considerations, right? So which settings do you need to set when you use this particular package? Which kind of choices do you need to make for parameters? So of course, one was the number of topics, but for this specific algorithm, you need to select an initialization method. So the model will initialize in different ways depending on the settings. Thankfully here, there is some guidelines. So the authors of the package, they recommend you to initialize what they call the spectral initialization. So at least here, there's some guidance. But again, here, different initialization will lead to different models, different outputs. And also because there's randomness involved in these models, you need to, or I always advise to use a fixed seed, which will then make sure that if you rerun the code again, you get the same outputs given the seed. If you don't fix the seed, anytime you run the model, it will even lead to different results, even with identical settings. So personally, I just always use 1 through 9. Not much I can do to mess around with that, like using the date or whatever. Then if I run it tomorrow, I could update the code, update the seed, and that would lead to different results. So just kind of to be disciplined, I just use 1 through 9 as the number. But basically my advice here would be, if you run these models, really have a close look at the documentations. Specifically in R, and I guess in quite some other software, if you don't specify options, it will take certain default choices. And sometimes that's not what's the best, right? So make sure to, if you use these models, have a close look at the help file. Yeah, go ahead.
I have a question.
Go ahead, yeah.
So if these methods are so sensitive that just changing the seed will provide a different thing, how do you know that what you're getting is useful and meaningful?
Yeah. So I think it's fundamentally, I think it first and foremost depends on what you want to do with it. Of course, if you want to do more qualitative interpretation of topics and they change every time you run the script again, that's a bigger problem than, say, I create some measure from it and the results from that analysis with the measure don't change, right? So then I think there's different flavors of sensitivity here. And of course, it can also change to different degrees. So if, say, the top terms shift a little bit in their ranking, that's less dramatic than if the topics completely change, right? But I just want to flag, it does change quite often. So it really depends very much on how you want to use these models. And I think there's a lot you can do as the researcher to flag, I made these choices along the way, and this is how things change within reason, of course, as I change things. So hopefully that addresses a little bit your question.
So let me summarize. So it is the obligation of the researcher to kind of go through the sensitivity. And I like how you're drinking wine in the middle of the presentation. And then the second thing is, like, if that's absent or the researcher doesn't do that, then we should be a little bit skeptical of the method. Is that right?
Yeah, I would say so. So personally, as I review topic modeling papers, I would indeed try to think through what are the key choices, right? Because some of these things, they don't lead to as major changes as others. So for example, in the code, at the very end of the code, I remove very infrequent terms, and then you see much more substantive changes, like the number of the best model changes and all those kinds of things. But I think in general, it's just good practice to document every step. These days you can host, like repositories or online appendices and the likes. So I think if you just show that you know the choices and then also be able to motivate the choices that you made, I think that's the first hurdle to take, I would say.
Excellent. Thank you. Super helpful.
So then in terms of fitting, right? So we made now some choices. So we chose the spectral initialization. We'll play around with the number of topics. So to see the best fitting model, I always fix this seed, etc. So you make those different choices. Then you would run a series of topic models typically to come to this decision on how many topics should I estimate? Unfortunately, also here, there's not really hard rules. There's some guidelines like this paper here. He hinges on like the size of the corpus. So if there's a few hundred to a few thousand documents, he advises to start between 5 to 50 topics. If you have very large or unfocused corpora, you would advise to move between 60 and 100. But if you read work out there, people also estimate hundreds of topics. So this is some guidance, but again, it's not gospel, I would say. I think most practical work would actually start with 100 topics, especially with larger data sets, and then work from there. But even with that considered, so you would run this series of models. So let's say 5 to 50. You still need to decide, okay, which one is the best one? Which fit statistic do I focus on? Recent work has highlighted 2 fit statistics that are especially useful for management research or social science research in general. And it's the kind of the intersection of exclusivity, which captures terms that are very important for one topic should have low importance in other topics. So they should be exclusive to individual topics, as well as semantic coherence, which means that topics are internally consistent. So the terms in the topics are internally consistent. As I mentioned before, there's many other metrics out there. So also in the package, if you just run the command to find the number of topics, it will put out like 5 different metrics. But those tend not to map very well on the interest that we tend to have as social scientists. So we tend to favor, I think, substantive meaning of topics rather than that they fit very well from a purely statistical point of view. And this is how the code would look. So there's this search K command where you specify, in this case, I want to estimate a topic model with 10, 20, 30, 40, 50 topics. It will run those 5 models given the settings. And then you can plot the fit statistics along different axes. And actually by default, the standard plot wouldn't even show exclusivity. So you would get the table. Again, just play around with it at home, I would say, or after class today. But basically, I think these 2 lines here are the most important, which give you this kind of graph. So here, what you want is you want to have the highest possible coherence and the highest possible exclusivity. So basically, the farther top right a topic model is, the better it fits. So you see here, this is with 10 topics. It's quite good on semantic coherence, but it's quite bad in terms of the exclusivity. And vice versa, with 50 and 40, it's very good on exclusivity, but relatively poor on coherence. So for me, this meant, maybe move between 20 and 30. So I went from 15 to 35 to just cover the range there. And that's what you get then. And here you see something like maybe 24, 25, 29 seems to be a good number. Again, this is what it is in uncertainty, right? So I can't say objectively 24 is better or 29 is better. You need to make some decision here. But I would say maybe 24 is the best for this run. But again, I could also then look at the topics, right? I could see, okay, try to code them, which of these 2 models, let's say 24 versus 29, yields the most meaningful topics. But this is already the substantive validation that would be needed that I'm actually not doing for this application. So now we have our topic model, basically. We know it's now going to be 24 topics and all the other settings, all the other data cleaning steps. And then you can run it, right? And then you can finally move into the real fun part, which is to generate theory from it. So you will be able to generate all these different theoretical artifacts that you can use for theory building and theory testing. And as I mentioned before, the topic model will put out 2 key outputs, the basic topic model. The terms per topic with the weights, so the different terms as they associate with different topics, and as well per document, how much do they load on the different topics. How you then use these, it really depends again on your research question. And I think this is really where topic modeling becomes more fun because you can use this in so many ways. It's multi-dimensional data along different axes, right? So it's really, really rich data that you can then interpret. But it really depends on your research question. So I myself have used it in this way. So as I mentioned before, kind of a deductive way. So this was in my own data. I was interested in distinctiveness. So how different are you from competitors? And kind of the typical approach in the stream would be, okay, you have different strategic dimensions, and how far are you off the average along those different dimensions? So in this case, the black bar were the loadings for a particular firm in my data, And this is in the industrial and graphic design industry. And this particular firm was very distinctive in terms of the topics that they used on their website, because they focused on kind of animation and advertising compared to the average across the industry, which is those white bars. So you can use this then to generate kind of a standard measure that other papers have used without using textual analysis to a new data set, basically. It's a little bit low quality, but again, this is the code that you would use to estimate this particular model. Again, there's different settings that I won't belabor here, but have a look at the documentation for this command. You'll see it's the STM command, but I'm not running a structural topic model. But as I mentioned before, the default for this model would be the correlated topic model with 24 topics. There's really many possible ways to interpret these topics, interpret the documents. I'll just flag a few. The most common one that basically any application of topic modeling would use is you would check, okay, what are the top terms for the different topics? So these are the top terms, the top 10 for the 24 topics. You can probably already see a little bit of an issue, because I don't think HTTPS, SV, Z, blah, blah, blah is a proper term, right? So an important term in a topic for me at this moment seems to be complete junk. So this for me implies, okay, I didn't do my job well in terms of cleaning the data. Some more work is needed there. Other topics look better, right? So let's see. So this number 7, for example, seems to be the boilerplate, how they might use your information as you visit the website. So it's not super interesting. This seems to be about research into using cannabis for, I guess, pain relief. And you can then interpret these topics. Yeah, I see the heads up for the time. You can also plot then in your overall corpus, how important are the different topics. So we see here topic number 5 is actually the most prevalent in our overall data set. So this one here, which makes sense, I guess, because this seems to be the standard kind of biopharma, who are we, who's the president kind of topic. And you see also this topic 1, which seems to be problematic because it contains this very messy word, is actually kind of at the bottom. So it's not a very important topic in our overall data set, right? So depending on how I want to use this model, this might be okay. I wouldn't say this is okay because this is really clearly not correct, but still depending on your purposes, it might be good enough to move forward. With the correlated topic model, you can also create these kinds of maps. So you can see how do the topics correlate in their terms. So here you see, for example, topic 19 has kind of overlap or correlates in terms of its terms with topic 9 and topic 22, and 22 then correlates with topic 4. So depending on what you want to theorize, this could also be a useful artifact. You can also use it in this way, right? So these are the loadings for the different documents. And I could again make this kind of distinctiveness representation of the topic loadings for every document. So this, in this case, is a document that loads very heavily on topic 17, which on the prior slide we could see contains these terms here. And then if I go to the website, I indeed see that this is a firm which uses genomics, genetics to map your gene profile and predict how your cancer risk and those kinds of risks are, and to make cancer treatments more personalized. So that works well with the topic. At the same time, of course, Myriad in this case is just the name of the firm. So again, this is a little bit problematic because I think ideally topics should be more general than firm specific. And then I can use this and throw this into a regression model. I was scared of including bad controls, so I didn't include any controls, but this is just a regression based on this distinctiveness measure using these topics. And indeed, I find quite a strong U-shape. I don't want to make too much out of it, but it's in line with what I found in the past. In terms of affecting performance. So you want to be either very distinctive in the topics that you emphasize or very indistinctive. And if you are kind of in the middle, that's not good. That's kind of a common finding in this literature. So working from this, it seems okay, that's actually pretty face valid, even if the topics had some issues. Okay, so I didn't have the time to go much more in depth, but check out the online materials. And as I mentioned before, I have there a check what happens when I remove infrequent terms, and that gets rid of those junk terms. What I then find is 29 topics fits better. The topics, of course, change quite substantively, but the U-shape persists. So depending on where I want to stop in my theorizing, I can actually get quite far with the basic model. So just play around with the code, see what happens. I guess I don't really have time to say much about publishing with these models, but I'll share the slides. But basically what I just want to flag are these 4 principles that I think are very important from Grimmer and Stewart. It's a paper in political science. And they specify, or they say, all quantitative models of language are wrong, but some are useful. These models are intended to augment humans, so they don't replace them. There's not a single best method for automated text analysis, and validate. I think that really goes to the core of how you should use these models in your own work. When you start using topic models, any kind of text will start to look like something you can use topic models for. Try to be disciplined in that. You really need to think carefully through, okay, is it suitable for my own application? So as you do this work, make sure to explain the method briefly. There's thankfully more and more prior art that you can work with. Crucially, really try to justify very well, why am I doing topic modeling? You could also quite often do content analysis. There's nowadays very popular word embedding models. Do you even need to do any sort of automated text analysis, or could you just do like deep reading and coding of these texts? So that's really crucial, I think, in terms of motivating why you're using this method. And as I mentioned before, I think it's really crucial to be very transparent about all those different choices that I flagged before. It can be in text partially, or can be in an online appendix where you have your full code. All those kinds of things, I think, really help build your case for your use of the topic model. I have a couple of slides here. I won't go through them, but these are just kind of more in-depth explanations of these different justification, reporting, and validation steps. So what would I typically report? How would I justify these things? But basically what I want to end with here is, I think it's a nice method. It's a nice tool to have in your toolkit to use for different purposes. It can be used for a lot of different strategy research goals. But how easy it is to use really masks a lot of its complexities and how sensitive it can really be. So as you use this, I think critical reflection on whether it's the useful tool or not, being mindful of all the different nuances, and really very careful validation of your corpus, of your topic model choices, and of your outputs are all really a must if you want to use this method in getting publications. So transparency, clarity in reporting, replicability, all those things I think are especially crucial here. I think if you do this well, the sky can really be the limit with this method. So it's really very useful, I think, to learn. But again, need some critical reflection as well. Some references, and other than that, thanks for your attention.
So we are out of time.
Yeah.
I really want to thank both Paul and Richard. I have learned, I'm an experienced methods person, and I learned a ton in both of these sessions. So gratitude. And this will all be online. And thank you for everybody attending. And there will be follow-up about beer. So, and with that, I think we'll sign off.